looking instead of looking at an exact, continuous time function x of t, let's look at an approximation x hat of t that is equal to the summation of x of k delta times delta sub capital delta of t minus k capital delta times capital delta. Okay. Now, what is this thing here? Okay. So x of k delta is the value of x at the integer multiple of capital delta. Okay. So this is the value of x, value of this x of t at integer multiples of capital delta. Okay. Now, delta sub capital delta of t minus k delta, right? If you recall, delta sub capital delta is the very short pulse that we used to approximate a delta function before. Okay. So delta sub capital delta of t is this rectangular, short pulse, assuming delta is very small, with magnitude 1 over delta when t is between 0 and capital delta and 0 everywhere else. Okay? So delta sub capital delta of t minus k delta is this square pulse shifted to time k delta and then multiplied by delta, right? So when this capital delta is multiplied with 1 over capital delta, then we basically have a rectangular pulse with magnitude 1. Okay. So this thing here is essentially a rectangular pulse with magnitude 1, okay, at time k delta. Okay. And this rectangular pulse, if you scale it by the corresponding value of x at this time, then summing these rectangular pulses up will essentially give you this staircase approximation of the original function x. So again, x hat of t is this staircase function here that serves as a approximation of this continuous time function x of t. Okay. So do we have any questions about this? All right. So if your continuous time signal x of t is sufficiently smooth, then we can expect that as this delta, right, as this delta becomes smaller and smaller and smaller towards 0, then eventually x hat of t will converge to x of t as delta goes to 0. And this delta sub capital delta of t, right, which is the very short pulse that we introduced before, converges to the delta function as delta goes to 0. Okay. All right. Now, suppose that we look at a particular value of t that is between m delta and m plus 1, that is between m capital delta and m plus 1 capital delta. Okay. So if you pick a value of t, suppose you pick a value of t here, between k delta and k plus 1 delta, then what is the value of x hat at this point? Okay. 那个王仁宏在吗？王仁宏在吗？ 那李云达在吗？李云达在吗？那李政伟在吗？
喂，是。
喂，嗨。那我刚才就想说，就是我刚才那个问题，就是说，如果我挑一个时间点 t 是介于 k delta 跟 k 加1 delta 之间的话，那 x hat of t 的值会是什么呢？
可以再说一次吗？
就是我如果挑一个时间 t，就是我图里面画的这个，就是我如果挑一个时间 t 是介于 k delta 和 k 加1 delta 之间，right？那它的这个值，它的这个值会是什么？
就是 x of k delta，因为它很
对，谢谢。
趋近于零。
对，没有不需要趋近于零，没有关系，就是说我只要挑 t 是在这个 interval 内的话，我只要挑 t 是在这个 interval 内的话，那 x hat of t 就是 x of k delta 这个值嘛。对，所以如果挑 t，如果说这个 t 在这个 k delta 跟 k 加1 delta 之间的话，那么 x hat of t 就会等于 x of k delta, right? Okay. All right. So this is what we're saying here. So if you here I'm just using m instead of k, right? So if you pick t between m delta and n plus 1 delta, then x hat of t should just be x of m delta. Okay. So hopefully no problem here. Okay. All right. Now, suppose that, this x of tau, right? I'm using the time unit, time index tau here, right? This x of tau, okay, is multiplied with this delta sub delta of t minus tau, okay? So this delta sub delta is a rectangular pulse, right? This is a rectangular pulse with a magnitude 1 over delta, okay? And because it's, time reversed, right, and shifted to time t, it would look something like this, right? You would have a rectangle that is magnitude 1 over delta from t minus delta to t, about this m capital delta here. Okay? Right. So if you multiply x of tau with this delta of t minus tau, okay, then the function you get is this function here. Is this function here. Okay. Now, if you take the integral, right, of if you take the integral of this function, right, you hope to obtain the area under this red curve here, right? And the area here can be approximated, right, assuming that delta is small enough, can be approximated by the rectangle at the same place, with a magnitude that is equal to x of m delta times 1 over delta, right, which is the magnitude of this delta function here. Okay. So this area the area, which is this integral of x of tau delta of delta t minus tau d tau, okay, is approximated by the area of the rectangle, which is x of m delta 1 over delta times the duration, which is delta. And this is just x of m delta. Okay. All right. So what does this tell us? This tells us that if you take the value of x hat at time t, you will get this value x of m delta, which is actually an approximation of the area of this function here. Okay. So by this observation, this x hat of t, which is summation x of k delta sub capital delta t minus k capital delta delta, right, k from minus infinity to infinity, we can approximate this by the summation of the integral x tau delta t minus tau d tau delta t minus k delta capital delta. Okay. And the reason is because we're approximating this value here, right, which is given on the bottom right corner, okay, with this integral, okay, okay, for a t that falls within the interval of k delta to k plus delta, because the value of t is confined by this rectangular function here. So if you recall, this part here is 1 only when t is between k delta and k plus 1 delta, and 0 otherwise. Okay? So for a t within this range, I can approximate x of k delta with this integral here. Okay. Now this integral, right, this integral has nothing to do with k, so I can bring this outside of the summation. And then when summing over these rectangles, right, over different time intervals, k delta to k plus 1 delta, k plus 1 delta to k plus 2 delta, and so on and so forth, the summation of these rectangles sum up to be a constant 1 function. Okay. So eventually, this gives you just this integral x of tau delta of t minus tau d tau. Okay. So then consequently, as this delta becomes smaller and smaller and smaller and eventually to 0, we know from the previous slide that x hat converges to x of t. Right? We know that this left-hand side converges to x of t, and that the right-hand side because this very short pulse converges to a delta function, the right-hand side converges to the summation, to the integral of x of tau times the delta function, delta of t minus tau d tau. Therefore, we get this equation here, which is basically the equivalent of the shifting property in the continuous time case. Okay, so in this part, right, we're trying to extend the concept of discrete time signals, right, to the case of continuous time signals. Okay, so analogous to discrete time signals, right, where we can view discrete time signals as a superposition of these unit impulses, we can approximately view a continuous time signal as a superposition of these very short rectangular pulses, okay, with delta going to 0 in the limit, okay. Now, this shifting property, right, you can actually obtain in a much simpler fashion, right? So the reason we went through the development before is because we wanted to draw some relation with the discrete time case. But actually, we were capable of obtaining this from the basic properties of the unit impulse that we introduced in chapter 1, right, quite directly, right? Because if you recall using the techniques in chapter 1, right, if you take the integral of x of tau d of t minus tau d tau, right, we know that when you multiply x of tau with a delta function at time t, right, you will only get a non-zero value at time t. Okay? So this integral should be equal to the integral of the value of x at time t times delta of t minus tau d tau. Okay? And because t has nothing to do with tau, I can bring x of t outside. So this gives me x of t integral delta of t minus tau d tau. And because the integral of a unit impulse function, right, the area of a delta function is 1, therefore this integral is 1, and therefore this is just x of t. Okay, so this is a simple way to derive the shifting property, right, x of t, okay, x of t equal to this integral here. Okay, using the basic properties of the unit impulse that we discussed before. Okay, right. So even though we could have attained this shifting property much easier in this way, but going through this development, it allows us to draw some relation with the discrete time case. So like I mentioned, by viewing it this way, right, we can view a continuous time signal as a superposition of these very short rectangular pulses, right? As a superposition of these very short pulses. Okay, so if the input signal is a superposition of these very short pulses, then the output signal should also be the superposition of the corresponding responses of these very short pulses. Okay, so again, if you view the input as a superposition of these very short pulses, then the output should be the same superposition of the corresponding responses of these very short pulses. Okay. All right. So suppose that we denote this h hat sub k delta of t as the response to this very short pulse at time k delta. Okay. So suppose that h hat sub k delta of t is the response of the linear time invariant system to this very short pulse. Okay. So then by the superposition property, the response to this x hat, right, which is a superposition of these very short pulses, is then a superposition of their corresponding responses. Okay. All right. Now, assuming that, for delta that is very, very small, approaching 0, right, we can approximate this very short pulse as a delta function at this time, and therefore we can approximate its response as the response to this impulse at time k delta, right? So if you recall, this h sub k delta of t is the impulse response to the response to the impulse at time k delta, right? Which is this impulse here. Okay. Then this y hat can be approximated as the summation of xk delta hk delta of t delta. Okay, so we're approximating this h hat with this impulse response h sub k delta of t, right? Then as delta goes to 0, this summation here, which you can essentially view as a Riemann sum, right, converges to the Riemann integral, right? So as delta goes to 0, this summation above, right, which is the summation of these, rectangular strips, right, is the summation of these rectangular strips here. Okay, converges to the integral of this continuous function here, which is x of tau h sub tau of t d tau. Okay. So this is the response, the input-output relation when we have a system that is linear. Okay. Now, if you have a system that is further time invariant, then this response to an impulse at time tau would then just be a time-shifted version of the response to an impulse at time 0. Okay. So this is saying that if your system is further, time invariant, okay, then the response to an impulse at time tau, which is h sub tau of t, would just be a time-shifted version of the response to an impulse at time 0. Okay, so this is all the same as before. Okay, so if you substitute h of t minus tau into h sub tau of t, in the previous slide, then the input-output relation can then be written as this integral form here. Right? So the output y of t is equal to the integral of x of tau times h of t minus tau. Okay, and this is conveniently written as x of t, again with a star or asterisk, times and this h of t. Okay, so this is the equation that describes the input-output relation in a linear time-invariant system. Okay, and this integral here is referred to as the convolution of the signal x of t and the impulse response h of t. Right. So do we have any questions for this continuous time case? 所以这个 continuous time case 这边的延伸有没有什么问题？
应该没有。
所以有没有哪一边觉得比较不清楚的？
应该没有。对。
对。好。那曾博勋呢？在。曾博勋有没有什么问题？
没有。
喂，在吗？
喂，在。
有没有什么问题？这边？
这边没有。
不好意思，听不太到。
就是这边比较没什么问题。
OK， 好。OK， 那我是蛮惊讶，大家没什么问题啊。对，因为这边其实那个我觉得就除非大家过去接触过 convolution 的概念要不然convolution 对于大家第一次接触应该都是有一些陌生这样子，不是那么容易了解。OK， 所以那不管就说大家是不是真的能够跟得上，就是建议大家回去这个部分稍微再复习一下因为这个后面就是非常的依赖这边的这个概念这样。Okay. Now finally when you write this input-output relation in this convolutional form, right, then you can interpret in the same ways as we did in the discrete time case, right? So you can either view it as first of all a superposition of the impulse responses corresponding to the impulses at different time instants, right? Or you can view it as the sum of the contributions of the input signal to a output signal at some particular time. Okay. All right. So tomorrow we will continue with some examples, and then continue to look at how we can describe properties of systems using this impulse response H. Okay. All right, thank you. 那我想今天就上到这边那谢谢大家。如果有问题的也可以提问，那没有的就可以离开，谢谢。请说。
其实这个不是，就是我不确定这样问对不对，就是我想问的是，就是在写 convolution 的时候，我们为什么是写成就是应该说在写 y 的，就是它的那个 y of x 的时候，为什么是写 impulse 的 response 而不是写就是 x 的 response？ 我们为什么会想要把它转换成就是 impulse 的 response 去 represent like y？
我不是很确定我有没有完全抓到你的问题，不过或许这用 discrete time 来讲比较好讲。所以这个就是这边最主要的一个重点，就是说因为我一个讯号其实是可以拆解成很多的这些 impulse 的这个组合嘛，对不对？对吗？对，陈佑还在吗？
我开一下麦克风，等一下。不是我的那个我知道它可以拆成很多个组合，就是
对
为什么我们把它我的问题是为什么我们把它转换到 y 的时候，我们是就是它是用原本的就是 x， 然后对应到它的那个 impulse response， 而不是 x 的 response 对应到它的那个 impulse。
什么叫 x 的 response
就是
对应到那个 impulse？
就是在这个系统里面是 x 跟 y 有对应关系吗？
对。
然后为什么我们不是用 x y 的对应关系，然后再去用用 impulse 去把 x y 的对应关系在那个点上取出来，而是要用就是impulse 就是那个 impulse 的 response， 然后再去取 x 的那个
没有，就是说 x 是一个 input， 对不对？那y 是它的 output。你其实就是说 y 是什么东西 depend on 你的这个系统是有什么特性嘛，对不对？对，所以那个 h 是帮助你算出不同的 input 会得到什么 output， 这样。
对，咦，
对，
所以就是把那个，我用就是比如说那个，就是把一个 transform， 然后那个 transform 已经包含在 h 里面了，这样子吗？
对，就是 Linear Time-Invariant System 很方便的地方，就是说它的这个 x 到 y 的转换，就是你说的这个 transformation， 就全部都隐含在这个 impulse response 里面了。对，就是你知道了这个 impulse response， 你就有办法描述所有可能 input 所对应的 output， 这样。对。
好。我还在想说，那为什么不干脆就是 y of 多少，然后去把 delta， 然后再把 y 跟 x 对应。好，没事，那没事了，谢谢。
OK， 好。